So maybe I'll just really start here introducing just really while people are flocking in. So I haven't really prepared anything formal, but definitely it's a great pleasure to have Carsten Schilde. It's actually Professor Carsten Schilde now. Just really very briefly, he in 2006, I understand, he got his degree in bioengineering in Braunschweig. And I really had the pleasure to meet him when he was a research assistant and then research group leader uh, in the Institute for Particle Technology, of course, part of the GCC in Braunschweig. But really, the highlight has been that he became the associate professor for particle simulation and functional structure at Braunschweig University. And I understand more recently, Heisenberg professor for digitalization for complex systems in process and production engineering. So it's very nice to see that Carsten is involved quite heavily with this so-called digital revolution, and of course, with his background in EPAT background in comminution and grinding, it's well received here at the GCC. His great involvement. We have seen plenty over the few last conferences. That's why we were so excited to when you actually accepted the invitation. So you came. It was a pleasure when you came to Brazil a couple of times here, and we met also in Germany when you hosted us. So also a great pleasure to see you here virtually yet another time this year. So I guess I don't. It's seven. Oh well, 04 here for me. So 4 or 5 minutes after the hour, I suppose we can get started. Please,
Okay.
floor is yours, Carsten.
Yeah. Thanks a lot for this very nice introduction. Um, and thanks for having the opportunity to presenting here everything what we have for the modeling of wet milling processes related to real-time process control. And this is a mixture of model-based control issues and of course AI. That means I will try to give you a journey how we come to this point where we are today. And this is a work in progress. So this real-time process control is a real work in progress program here in Braunschweig. So there are still points to do. But I do my very best to show where we are at the moment. And I would like to have a classical introduction of my research here at the Institute. And this is related, of course, if we are dealing with particles, with these process structure property relationship, where we have the particles on the one hand, and on the other hand, we have our customized products, and in our case here coming from the comminution process. And in between, we have several production steps with, for example, related to formulation, grinding, and classifying. And all these steps intercorrelate with each other and having an effect on the structures at the end of the customized product. And if they have an effect on the structure, of course, they will also have an effect on the application related properties. And this is independent if I have kind of an aggregate, a structure of a coating for lithium ion battery coatings or whatever. So and the question is how now these different processes depend on each other's and how the process parameters affect the structure, and the structure at the end, the intermediate product features and the final product features of our product. And of course, in the past, we have started with a lot of the physics-based modeling in order to derive these equations and get this model. I'm focusing here on the model since if we come to real-time control of steered media milling, of course, we can just do it with a target value and trying to adapt the target value based on a certain measurement. But the more efficient way is to set a model behind, since this model can predict states in the future, and then we get a much more precise and faster modeling control result. And that means the process modeling is very important. And if we take a look on the past, we have, Marcelo, we have models from you, we have models from Arno. There are a lot of models on grinding processes. And we have this traditional way, and then at a certain time, we get additionally the numerical points within the modeling. That means we are able to get, for example, stress energy distributions derived from particle simulations, which we can then add to the classical models to enhance them, to further bring them on the road, and also to make them more realistic. For example, geometry dependent, or depending on the throughput and whatever. And these more realistic models help us now to get it also usable for process control. However, also these models have, it's challenging to use them directly for process control. And that means we have this additional data-driven approaches to bridge often the gap in between the mechanistic models, even with numerical aspects, and then going to the real behavior of our mill. And if we think this way a little bit further, we are coming to hybrid modeling. And if we further think this way, we are coming to, for example, transformer methods. That means bringing also context within our modeling issue, and also context-related knowledge within, for example, the process control. And that's something I would like to address today. This road deriving models and then coming to the process control. That means in my case, we have the experiments and we have the corresponding modeling tools here, the numerics shown in this slide. And if we going to data-driven methods, we have it here. And these methods now assist our model development, and the model development is then used for our real-time process control. So if we're talking about these newer methods, we have also our challenges. I've shown this slide before. It's just to have the same basis again. But typically we have black box models if we talk about working with data. And if we are working with data, we have a lot of challenges if we talk about, for example, grinding experiment or grinding processes, since we are often in lack of necessary data sets. That means we need to think about how to get enough data, how to make kind of intelligent experimental setups, how to measure everything we need for the modeling. And also now we are having on top, not only we need to measure everything for set up a model, we need also to measure everything online in order to make a sufficient process control. That means normally we need now values like what about the viscosity, or what about the particle size distribution directly online, and with a very high resolution. That means we need to have a resolution of maybe 1 Hertz in order to get also a fast process control and a real-time process control. If we put in a measurement system which have a reaction time of several minutes, then of course our process control will also have a reaction time of several minutes. And that means these aspects here, these demands on dealing with data-driven methods, are getting more and more important if we are also talking about additional online process control. And of course, if we know something about our process, if we have a kind of not black box modeling process, then we can also transfer models, we can react to changes in the feed, we can react to changes in our production setup or technical setup of our milling process. That means if we are deriving models, physical-based models, and have just a short addition, which are data related to make it real-time available and usable for a real-time control system, then we are in a good mood. And this is just to remember it. And also coming from the past, we are using AI in order to predict, for example, the medium particle size at a certain time and under certain process parameters. And we extended this just black box prediction also to predict the whole particle size distribution at given process parameters at a certain time within steered media modes. And that was the basis to work further on, including now also with existing models, for example, the Quade Quadis stressing model and combine this prediction with the Quadis stressing model. Here, in this case, we have this issue that we can predict at a certain time our real particle size distribution. But if we do changes during the process, then it's getting harder to obtain it. Then you need other methods. So the pure black box modeling using neural networks are not working anymore. And I think all of us know that if we are starting with a certain particle size in a wet milling process, and with decreasing particle size, and maybe at a similar viscosity of our suspension, we can reduce the stress intensity to go further down during our milling process. And that would be nice if we have an intelligent process control that real-time adapts to the given measurement parameters, for example, the tip speed. And with a reduction in tip speed and stress intensity, we are getting an energetically more efficient, for example. That's one goal. That means how to realize it. We need our mill. We need a certain kind of a model which need to be adapted due to simulations, this mechanistic models working with real stress energy distributions, for example. And on the other hand, we need from the experiments also our online sensors, at least soft sensors, which gives us with a very high resolution our particle size distribution as well as our viscosity, and at least a minimum medium particle size. And then we feed this information with a population balance model. And our goal of this project here is not to have a process control, a real-time process control on one particle size, but on the whole particle size distribution. That means we want to control on the population balance model. That's our goal, and now I will show you step by step how we reach this goal, and then I have a longer outlook what's coming up. And for our process control, we are using a very old seared media mill. We have the PM1 from Bühler, which is a very old one, but since it's a very old one, we can change whatever we want, and if the mill will be break down in a certain point, it doesn't matter. And in our case, we have the mill, the grinding chamber. We also have a digital twin for the CFD modeling. And we have some online sensors, which are hopefully, I will try to set up the laser pointer, which is here depicted here in this area where we have this measurement device, which is an ultrasonic particle size measurement system with very high time resolution. However, ultrasonic particle size measurements are maybe not the best particle size measurements when it comes to accuracy of the real particle size distribution. That means we need to think about, is this what we measure, the real particle size distribution, or do we need a kind of calibration to offline measurements? And I come to this point in a few minutes, but here is our real experimental setup. We have our seared media mill, where we measure velocity, torque, the power intake. We have the volume flow measurement. We have a torque measurement of our steered vessel. So we have this vessel in our circuit operation mode. We measure our pH conductivity. We have a heat exchanger. And we have here at the bottom our particle size measurement device. What we don't have online here is a measurement system for viscosity. However, we have the torque, for example, of the steered vessel, and we have the particle size distribution. And what we know is that the viscosity strongly depends on solids content, which doesn't change, and the particle size distribution. And we have a kind of at least 2 torque sensors, which gives us at least 1 point maybe of a soft value for the viscosity. And with this measurements, we then work further. Here's some how the flow through the system works, and through the measurement device and the circuit operation mode. And we measure now the particle size distribution with this Opus measurement system, and we measure the torque on our stirrer in the vessel and within the mill. And what we did now is we get all these different data from our experimental setup. We get also the opus measurement, and we get the torque measurement from our stirred vessel. And now from time to time, we take samples. And then for a given suspension, we measure our samples offline in an ideal case using dynamic light scattering, and in this case with nanofox from the company Sympathec, and we are using a rheometer in order to measure the full viscosity curve depending on the shear rate. So not only one point, we are measuring a stepwise increase shear rate and the viscosity, since we have the shear thinning behavior of our suspension. And what we did afterwards, we are now using the opus values, which we get online as a kind of a soft sensor with here x10, 16, 15, and so on, all these values, and we translate them to the nanofox, and then getting the real particle size distribution within our online system. So we adapt just a simple artificial neural network, which doesn't make anything else than having a translation function between our online particle size measurement and the real offline particle size measurement. And that means now we have in our system online the real offline measured particle size distribution. And then we did something else on top. We just trained another artificial neural network, which now has the torque of our sensor from the stirrer. And we know that depending on the particle size distribution and our solids content we put in, we have in our feed, this defines our viscosity, our shear thinning behavior, depending on different shear rates. And if we have the torque as a kind of a one-point calibration together with the real particle size distribution, we can also have a transfer function to our viscosities measured in a rheometer offline. And this works quite well. So on top here in this slide, we see the measured and the predicted values of the particle size distribution, which have a very high accuracy. And at the bottom, with a little bit less accuracy, we see the prediction of the whole or the viscosities at different shear rates. That means the shear function of our suspension. And that means here's something more, the feature analysis and importance of different features. But what we have now is we have now a real-time particle size distribution and viscosity at different shear rates, which we can use for our modeling and our process control. And when it works is seen here. So we have and the red line and the dark black line, which are they are laying. It's hard to differ between these two lines. So I think we are doing well with our transfer function coming from the soft sensors to the real-time viscosities and particle sizes. And this is now having the different x10, x50, x90 values online during our grinding process. So now we have an online sensoring of the whole particle size distribution with a high resolution and also the viscosity. And this is the part we need for process control, for the real-time process control. For the model we want to set behind, which is then used within the grinding population balance modeling approach, we want to introduce a real stressing energy curve or intensity curve of our mill within our population balance model of the machine function, which is then related to the breakage rate as well as the breakage function. But the breakage rate, there we want to introduce or implement our real stress intensity distribution. Therefore, of course, this is also known for a lot of people here in this audience. We can do CFD, DEM simulations in order to derive this stress energy distribution. And you have seen this slides before. We can also calculating or dividing our mill within voxels, making slides and dividing the slides and with a certain resolution, having at least maybe 30,000 voxels within our mills. And then we can make this prediction of the stress energy for each voxel, summing it up and then getting the whole stress energy distribution for the mill. This is here shown for an easier example, but it was also done for these other mill, the Bühler PM1 I have shown before, but the resolution is not so perfect at the moment. So I step back to this slides here. And based on this simulations and the three-dimensional modeling of the three-dimensional stress energy distribution within the mill, we can predict every stress energy at every process operating point within the mill. And this we can then use afterwards for modeling the stress energy distribution depending on the process parameters. Of course, this is also a result you have seen before, where we can take a look on how the relative velocity within our system depends on different regions. For example, here the outer region was investigated within the mills and compared to the prediction with AI and the simulation. Here for this prediction we used typically time-dependent convolutional neural networks, that means LSTMs, which has a very high accuracy in the prediction. We can also predict within the holes where we have, of course, much larger relative velocities between the grinding beats, and these relative velocities give us when our stress energy distribution is a certain set of parameters within our mill, which is given in the next slide, where we have the relative velocity cumulative distribution within the mill. On the left side, you can see an old version where we have a standard artificial convolutional neural network used. On the right side, we are going more and more to some additional training procedures with much higher artificial neural network accuracies. So here we put in a genetic algorithm in the training within our prediction or artificial neural network modeling system. This can be done also for the dry grinding. We also applied it for this vertical steered media mill, but this is just an add-on where we can have also some simulations which are here given on the bottom, for example, and the prediction on the top. And if you compare this in different heights where we make the cuts through the mill, it looks quite good in the prediction. And also if we have a horizontal cut or a vertical cut through the mill, it looks also very good. And if we compare now the relative velocity distribution, now the density distribution here, it's hard to define any difference here. So this is the standard modeling thing we do, and in order to reduce the simulation times and effort, we use again artificial intelligence or machine learning tools in order to be much faster in the prediction of our stress energy distribution. And now the question is how we can model the stress energy distribution depending on the process parameters. And here I have just, and so at the end, we get data coming from artificial neural networks, from simulations, from experiments. And the question is now how we derive our physical-based model out of it. So that's here given by this slide where we have in the center. I think you should be more explicit here in step 2. This is often the case. We do experiments, we do simulations, and we don't get the model, for example, for the stress energy distribution from our simulations or the whole population balance model. On the other side, we need this model for process control. And that's our approach is here to use a kind of a hybrid modeling framework. I have this slide just to show you in principle how it works. And then the framework will be shown on the next slide. But in principle, it works that we have input data coming from simulation or experiments, which will be then post-processed, stored additional with metadata, and within a database, where we have a particle size distribution, the structures, the process parameters. Then we typically train neural networks. And nowadays, we are not using neural networks anymore. We are using graphical attention networks, which are much better, since the reason for doing this is creating out of simulation results or measurement results artificial data, since modeling tools working much better if you have artificial data. That means we are doing just a kind of intelligent interpolation of our data. And previously we did it via artificial neural networks. Nowadays we are doing it with the help of graphical attention networks. And then we are creating from 100 or data sets, maybe 10,000 data sets, and then we are going into our modeling tool. And the modeling tool in our case is based on a genetic programming. I will come to this in the next slide. And this genetic programming will give us then a certain equation. And this is shown here in this slide. This is in principle how this tool works, the hybrid modeling framework, which automatically derives model equations. And here on the bottom right, we have our model equations in a kind of a tree structure. And this tree structure exists several 10,000, 100,000 times. And between these tree structures, we try to find the best one via using the basics of evolution with selection, crossover, and mutation algorithms. So we find the best trees, make a crossover between them, and then mutate them, make daughter trees, and then find again the best ones, having a loop like in the evolution in order to get the best equation. And then we have several tools now in order to bring physics inside. For example, we are adding the p-theorem, or we are adding shortcut models from literature, which could be a Tavares model or a Quade model or other models. We just add them in a library, and then if they are part of our modeling solution, for example, for stress energy distribution, this will be forced to be recognized in our final equation. This is in principle the workflow. This is how the program looks like nowadays, where we have here our graphical user interface. We have something that we could put in the data. We could also have a feature analysis of data using different algorithms in order to pre-reduce the features to the important ones. Then we are going into the modeling step, and the modeling steps is all about these things here. So all of these are different methods with the goal to bring in physics. So for example, also this tool does everything 1,000 times in parallel. Take a look on if, for example, certain fragments will be found again and again, and then push all of these systems to use this fragment, for example. So there are a lot of different tools, and in combination of all these different tools, we are able to bring now in physics and derive equations, which are here shown in principle how it works. And we did this, or we applied this framework also to our steered media milling process, in order to fit, for example, the parameters of our population balance methods depending on the stress and intensity distribution of our mill. So we use this framework in order to derive our models for the breakage function and the breakage rate, depending on the stress energy distribution. And here what we can see here is, for example, some errors, how they evolve over time and certain parameters within our system. We also want to extend this system. I will show this later, but this is in principle how we come to our population balance model. But I cannot show the model here up to now since I'm still missing the information from my PhD students here. But how to go on afterwards? Afterwards, we go within or to our mill, and the idea is now to have a model. The model, like a population balance model, which predicts the whole particle size distribution. And of course, we will have a target value. And to reach this target value, we can apply different control strategies. So there are different ways to get to this point in the future. What does it mean? We take a look and a short step in the past, apply the model to our grinding process. So make a fit, then the model predict based on that fit possible future steps if we now make a change. So that means not only to predict a certain point in 1 minute, but the whole evolution, how the values evolve in the future. That means we have a continuously adaptation of our future states at different time steps in the future, and depending on the combination of different time steps in the future, the model will choose how to adapt the process parameters now. And this can be done by in principle, by two possibilities. One is to have this population balance model. The other thing is to just train again an artificial neural network, which has all these input parameters and the resulting output parameters over time. And then having a kind of a model predictive controller on the one hand, or a neural controller on the other hand. And I would like to show both of them in the next few slides, how they work in our case. So this is a little bit the visualization, what I already talked about, to predict coming from the state now a certain stage in the future, and the green line is the adaptation. Based on this adaptation also of the green line, using a kind of a sliding window for the process control, we then again predict the next steps, and this is done further and further. And then we choose one control strategy in order to reach the best target values. And as I told before, this could be done by a model predictive control. In our case, since we have a population balance method, it's a nonlinear model predictive control strategy. And this is not done by us. This is done here by our project partners here, which are professions in machine control. We are not. And they are using a kind of an alternating direction method of multipliers. So what is this system doing? The system uses the population balance method and bring all dependencies down to several blocks. So for example, the dependency of our final result on the tip speed, the dependency of our final result on the throughput, or the other parameters like the temperature, for example. These are sub-models, and these sub-models will be then solved independently. And why is this necessary? This is necessary in order to be fast. We need to have a process control which is very fast and bring it down to easier subtasks with only one parameter dependency, and then put everything together on a larger scale is much faster than try to solve the whole population balance model during time online. And that means the derivation of control strategies depends much on how to which algorithms you use and what does it cost computationally. And this is a very fast computational approach to come back then to the real online process control. Yeah, this is just the background here, but the principal meaning is dividing our population balance model in sub-problems where we only have one process parameter we can control as a control variable, and then putting everything together, having an optimization on the larger scale depending on the sub problems. And if we do so, we started here with an easy population balance model. So we make a step back, and that's what I said at the beginning. We have the model of the population balance method within that steered media milling coming from previous PhDs now and adding the stress energy distribution bit. But this is a very complex population balance method. And we are now at the stage where we are able to have a real point or real process control based on the King's model within the population balance method. So there are some steps to go to come then to the real population balance method we already have, but it need to be divided into the sub-problems. Then we need to define a solution, a derivation of these equations in the subspace, put them again together on the master level, and then having again a process control algorithm. But we started with everything, and this is the state we are at the moment, where we can derive the King's model and putting it into sub steps, having the input of tip speed or throughput. And here is just a simple example where we adapt during the process the mill speed and having a kind of target particle size distribution with minimum energy input. And what the mill is doing at the moment, it continuously reducing the tip speed during the time in order to achieve a certain size class. It's just named here with classes. So the class is corresponding to a certain particle size. And this is then our goal here, the target class, which is given here by this red dot on the top. And the process control strategy is now here working to achieve this goal with minimum specific energy input. And they compared also this approach to other standard algorithms which can be used for process control. For example, this operator splitting quadratic program algorithm, which works also very well, but is very time consuming. And we are reaching similar values, but with less time effort. This was related here now to the, this is related to the nonlinear model predictive control. But what you can also do is you can use the same strategy as given here in the slides before, and here is shown in the upper left of this slide, using not a physical inspired population balance model or the King's model. You can also just train an artificial neural network and also make these predictions. And this is presented somehow here on this slide, where we use a kind of a neural controller. We have also the sliding window. The neural controller predicts also depending on different possibilities for the process parameters, future states, and also choosing the right one depending on the evolution of particle size in the future, but now with a black box model in this case. Of course, the other one is much nicer. This one here can be much faster adapted. This is something we do by our own in the past. And here we apply it depending on the temperature. So we set up different target values over time. And then we apply our artificial neural network. That means neural network controller to our system, and then trying to get our control or our target value. And you see here the control variable of the temperature. It matches very well to the target value. So it works also and has also huge potential. But I think if you be more sustainable and reliable, the nonlinear model predictive control is a much easier one. And that's in principle what I wanted to show today. There is our actual state on real-time process control within steered media mills, and also doing some optimization tasks during the milling process. There's still a lot of things to go, and there are a lot of possible things we could do, a lot of potentials. One potential could be to also take into account for the modeling part, deriving models which can be used for model predictive control, transformer models. So here is a principle framework how transformer models work. We have certain word vectors. For every word, we have a certain vector. These vectors will then located in a sentence via position vectors. And then on top, we have attention vectors, how different words interact with other words and other vectors depending on their meaning. And this attention vectors on different scales are the ones who make this language models, this large language models, so complex and so large at the moment. Since we have certain probabilities that every word corresponds to another word, which is shown here in principle on this slides. So we have the word vector, similar words have similar vectors, horse, cat, bird, sun, moon. Then we have a positioning vector on top, which defines where this word is defined or placed in the sentence. And then we need to relate different words to each other, and this is done by a huge matrix of probabilities. So this statistical vectors will relate it to each others in a huge matrix. And this is also depending on the query we asked our system. And that means, for example, the paradigm it has high correlation, for example, where AI paradigm has a lower probability to be mentioned under a certain query within our system. And the question is now why I mentioned this here. Since you can now use these transformer models, and in general, a ChatGPT approach cannot be used in process engineering or steered media milling. But what you can do is you can make not from ChatGPT, but from open source transformers like Llama 2, Llama 3, you can make experts. You can put a database add-on that is called embedding or LangChain, where your transformer is using a database in order to increase his knowledge in a certain research field. But you can also retrain the whole transformer, which is then called fine-tuning. And then you make an expert. You can use all literature existing in the field of communication and train it inside this expert system. And then you have an expert transformer model which can help you to derive models. If you ask the system what kinds of models exist in dry grinding, for example, and he immediately has everything there. And he has also every information which is not written in a formula or written in a table or in data. You also have the context knowledge. And this can help you to find new models and maybe in future also to make an intelligent process control without setting the user for minimum energy or whatever. So these are possibilities. And this is here at the moment our framework, how we do our training of our experts. So we have Llama 2 and Llama 3 transformer models, which has also some add-ons regarding consistency. They need to give us consistent answers. We need to check it. They have access to databases, also using transformers for intelligent search within databases. We have online search, and we can also ask traditional transformers for their opinion. Of course, we will have consistency at this, and this is just one expert. And then we now can put several experts in a row and kind of discuss an issue. We could have a modeling expert, a grinding expert, a simulation expert, and they can also connect it to math experts. If we have some equations, they can solve these equations. And on top, we put some managers. And the manager organizing the sub-transformers. This is exactly what we realized here at the moment. This is called mixture of experts approach, where we have a manager who controls everything. And the experts could be now a knowledge expert, as it's shown here, for the grinding process, combined with the mathematical transformer model. He can solve, for example, calculate the power or energy requirement online with an agitator mill here. This is our prompt. And then we have within our manager system a chain of thought. So the prompt will be deferred into different process steps which needs to be done, which are given here. You can for calculating then the energy, and this can be then used, for example, for minimizing the energy or the time within the milling process. And in this case, we are able to reach 100% of accuracy, but there are a lot of more possibilities here. You can also think about one who is doing the simulation, or one who is doing the machine learning, or you can also think about innovative, creative transformer methods, which is also possible nowadays. So, and this is then the idea we are focusing at the moment, our mixture of experts system. You have seen the one who exists at the moment, but we are working at the moment on the one who is doing automatically our modeling issue, where we combine our framework with the software to our large language model, or we already have done to combine a transformer model and to close the loop to Fluent, for example, to realize simple simulation issues regarding the shear rate distribution in a steered tank, which can be done by the transformer. You don't need to open Fluent anymore. So you have a PyFluent, which is a Python-based possibility to work with Fluent, an interface, and you can write plugins, and these plugins can be then used by the transformer system to work with Fluent. So you put in the prompt, give me a simulation of the reactor shear rate distribution, then he will start via the plugin PyFluent. PyFluent will start Fluent, and then you can do simulations. And then he will ask you for the CID file, and then you can do it. And just the last minute I will use to show how this then all can interconnect. You can create such a system. We call it at the moment, it's coming from the German one here, Anlagen AI, but we are shifting to particle operating system. You can put in all these issues in an intelligent system with a lot of apps, for example, and these different apps could then, during modeling issues, could have the knowledge transformer involved, could have also some ensemble learning methods involved in order to get more information on the process. What do I mean? So this is just our actual app store here for process operating system. But within these app store, we have several apps. For example, a data modeling toolset for hybrid modeling, I have shown before, but also for standard black box modeling using hidden Markov models, Kier, nearest neighbor, gradient booster systems, artificial neural networks are in this app. You can have also some product analysis, or we have here an app for a mill digital twin. This is a little bit different from the one I have shown before with this model-based control. This one here is just related, I will jump to it. This is a modeling part, to a real-time monitoring of our mill. So we have it within or adapted to our mill. And then he predicts the necessary energy depending on certain target values. We want to reach a certain particle size distribution, and then he predicts how much energy we need to derive this goal, but only depending on all grinding experiments he has ever seen. So this is a kind of a huge combination of neural networks which work together and leading to it's called ensemble learning approach, which then can be adapted to the actual process within the mill and is continuously learning on what he's doing now and then predicting values in the future. And with this last outlook of this approach and tool, I would like to finish my presentation. And thanks for the time and having the opportunity to present everything here. Yeah, thanks a lot.
Thank you, Carsten. Very interesting presentation. And I'm sure we have some questions here from the audience. I have a question here from, you can open your mic.
So maybe an overflow of all these different things. Yeah, I try to put together.
Well, Marcelo raised his hand and Mamoudou also, but Marcelo, yeah, go ahead.
So, well, the technical problems from Mamoudou are being resolved. So, fantastic presentation, Carsten. So, definitely you show that there's quite a lot of opportunities and pathways, I suppose, when you look at the AI in the context of communication. So, really great presentation and definitely very exciting for people who were thinking about going into this. I think there's one message I understand from your presentation, that you don't really have to give up on your background as a physical modeler and experimenter in order to go into these areas. So this means that this hybridization, there's plenty of opportunity there. My comment is really that I think one of the challenges, just one small part, but it's perhaps an important one, is that when you look at things such as extreme conditions, for instance, a very simple one, that let's say you have an oversized feed coming into a stirred mill. In that particular condition, you see weird things, which is concentration of coarse material coming in the mill and things like that. And that very particular condition requires you to capture, for instance, in the DEM simulation, very particular collision spectra, which is very few collisions of high energy, which may or may not be well captured using this type of approach. So my comment to you is that one challenge I see in this, and it goes into fitting information, for instance, from dispersed information like collision spectra, is how can we teach this well enough, which areas are critical? Because on the average, I think these tools are absolutely fantastic, but I'm concerned about the extremes of the domain. What's your experience with that?
Yeah, maybe first of all, again, I would like to point out that it's everything of this is work in progress. And maybe if you take a deeper look, you see sometimes there is a bridge missing or a bridge only halfway done. So this is yeah, a work in progress. And if you think about that, and with your comment, this is the major problem. So we can do it for standard grinding progress, and of course we will capture a certain range of varying feed, yeah, larger particles in the feed with a certain range. But if it comes really to outliers, then of course, if it will be not captured within the model, either in the just black box model or in a kind of more physics-based model, you have no chance to then use your model predictive control or your black box predictive control to get this running again. So this is an additional point which is not solved within this approach. Yeah, of course, you can enhance the approach and put in more and more on different stages, but makes it, on the one hand, at a certain point, the process control is getting more and more complex. That means you need more time to predict future states. That makes prediction slower, that makes adaptation of the system slower. That could be an issue. That means we have limitations here. On the other hand, the issue is if you have an oversized feed, then it depends on the material which kind of portion of grinding events are active. That means you also then need again to put in the material function into account, and all this. Oh, I don't know how to deal with it, and that's the original limitation at the moment. If you have only one material, you can go to this black box approaches. And of course, then it will be an easy task. However, you cannot change the mill, you cannot change the material, so that's normally not what we want. But you can get a very stable process also with some issues, also maintenance issues. So in our model, no maintenance is involved at the moment. If we have changes within our bearings during time, then we will have changes on the torque. And now we use the torque to predict the viscosity. The viscosity is used for the damping, has an effect on the particle size. So at the moment, we don't take this into account. But of course, we should. But we are just at the beginning, and we are so far away from or capturing all these effects.
Thanks a lot.
More questions? Malcolm, please. You're muted.
Okay, Carsten, that was great. It's so far ahead of what I've been doing that I'm struggling to keep pace. I'd need months of education to catch up. But what I like about what you've done, and Marcelo hinted at it, is doesn't actually do the scientist side of a job. It's bringing the best scientific foundation you have and basically enhancing it is, I suppose, the way I think about it. Had a couple of questions quite high on my mind, but one I might jump into is that you said you could get them to be trained by existing papers and data.
Mm-hmm.
The problem is, contrary to what a new PhD student thinks, 70% or whatever are poor or rubbish or outdated or have been superseded. So and same happens with data. There's lots of poor data. How can we help screen out so that these experts and formers we're going to use are actually real experts?
Yeah.
They haven't been trained by dumb people. They've been trained by the best in the world, or the outputs of the best in the world. I'm really interested in that.
Yeah, that's a very interesting question, and this is and there are now several aspects we need. So first of all, if we train, just an assumption, we train every knowledge on grinding within maybe several experts, a dry grinding, a wet grinding, for minerals, for whatever. We do several experts, we put them in such a mixture of experts approach. Then, of course, I would expect from my personal point that this one is much smarter than I am. So the existing ones we train, they are smarter than I am. But and even with the smallest transformer model, so the Llama 2 model is a very small one, and they give better answers to questions than I can do. And even with a few books on particle technology, so if you just put in 10 books on particle technology, they give much smarter answers than I can do. Okay, that's another thing I need to think about by myself and by my own. I think that's a good point, that a new PhD, which has no experience, already could dive very deep into the topic and has a kind of an assistant. It's a kind of an onboarding system. But also in the modeling, if you when able to put in some hybrid modeling tools which automatically gives you equations, and you have a complex systems, and our processes are getting more and more complex, then you get, it's not having the ideal model. It's, oh, this is given by the system. What could be the reason for that? And then you come still back to, you need the knowledge, you need to think about that, you need to derive then the basics and the basic mechanisms behind that. That's maybe not given. Sometimes maybe a transformer who understands the context could say, this is given here, that should be recognized in an equation in such a way. And this helps us. I think it's a huge help in the future. And now we are coming to the point where we need to think about, we have a lot of rubbish. And now we are training a lot of rubbish in our system. If we are training 1,000 publications in our system and we say, okay, maybe 10% are rubbish, just an assumption. And we are asking the system a question where we have 9 publications, which giving the right answer and 1 the wrong answer. Since the transformer method is based on statistics and probabilities, he will give us, in most cases, the right answer. And you can put in cluster voting algorithms afterwards. If you have several experts, they all have an opinion. When they try to cluster their opinion and they say, okay, we have a few outliers. You can also take a look on the few outliers if you want to, but this helps a little bit to exclude the rubbish, even if you just trained it in. You trained it in, but it will not mention anymore since you trained much more information on non-rubbish literature. But you cannot exclude that you get a rubbish answer. And now we need to think about, if I ask an if you ask an expert on a certain topic, and he is not very deep in this certain question, he can also give you a rubbish answer. And if you ask 10 experts, maybe 1 or 2 will give you a different answer. That means we have a similar problem when asking colleagues for a certain question, but we have no control anymore about it. We're losing control on the answer, and we're losing also control on how to check how trustable or reliable, how transferable, how robust is the answer. And that's something we are also thinking about, how to come back to this point a little bit if you're using node transformers. This is a huge question. I cannot answer it.
Thanks.
If we have a grinding expert once, a huge grinding expert, we will send it to you and you can give us feedback if it's a good one or a bad one. That would be thing. If we train a grinding expert or expert system, we send it to all the GCC members and waiting their feedback. That could be a proof of concept.
It could be more challenging, do it live. A live discussion. That would be fun. Thanks, Carsten.
Yeah, thank you.
Thank you again, Carsten, for the very interesting presentation. And thank you all for attending today. So I think our next seminar will be maybe February or end of January. So we don't have the GCC December seminar. So thank you all for attending, and the recording will be available in our GCC YouTube channel maybe by then, later today. Okay. Thank you all for attending. Thank you, Carsten, again.
Thank you very much. Goodbye.
That was excellent.
Thanks, Carsten.
Thank you. Thanks for having an opportunity to present this finished work.
Great.
Thanks, Carsten. Bye.
Thanks.
Bye, fellas.